Okay, welcome to 7-4 solving exponential logarithmic equations. The first property that we have here for any positive numbers x, y, and b not equal to 1, then log base b x equals log b base y if and only if x and y are equal, because you've got the same bases here. So this really helps us in doing this. We've got an equation here. 2 to the x minus 3 equals 85. Log 2 to the x minus 3 and log 85. We just take a common log on both sides. What you do to one side, you can do to the other. And what we find here is that we can move this raised exponent out here, x minus 3, by the property we just proved in the last lesson. Now we can take x minus 3 divided on each side of the equation, and we end up, it cancels here, and we have I take that back. We wouldn't do that. I forgot, we're solving for x. Circle your x, go back up, circle your x, draw your line down, I'm getting tired. Okay, we're solving for x, so what we want to do is we want to divide by log 2. Get that x by itself. I'm still wanting to put x. So sorry, you guys. Log 2. So now we have x minus 3, log 85, log 2. We're going to add 3 to each side, and we get log of 85 divided by log 2 plus 3. And we can totally do this in the calculator. So we turn it on, because we have log base 10s here. We have log 85, close that parenthesis, divided by log 2, close that parenthesis, plus 3 equals 9.40. 9.40, 3 decimal places, 9.3, so it would be 9.409. Okay? Kind of neat how we can solve these. So now you know 2 to the x minus 3 equals 85. You could plug in 9.409 in there, and you have roughly what it would be. How do you use the power property of logarithms? Well, it moves the variable out of the exponent. That's the main thing, is it brings it out to the front. That was the move right there. Power property of logarithms. How can you use estimation to check if your answer is reasonable? You can actually plug it into the calculator. Put 2 and then raise it to the parenthesis n.409 minus 3 parenthesis closed, and then hit enter and see if it comes out close to 85. I'd highly recommend you do that. Okay. Next page. This time, we're going to take the natural logarithm of both sides in order to solve a real-world problem. So we have Adam has $500 to invest in 4 years. He wants to double his money during this time. What interest rate does Adam need for this investment, assuming the interest is compounded continuously? Really, we want to be able to do this kind of a thing with our own money. So we've got $500 we're going to start with, and we want to double it, so our A value in the end, we want to be at 1,000. So the equation would be 1,000 equals 500 times the E raised to the R, and then the T, let's see, does it say, yeah, 4 years. That's all. Okay, so we come on down, 1,000 equals 500, e to the 4rt, would divide each side by 500, and we'd end up with 2 equals e to the 4r. Now if we do LEN on each side, the LEN will cancel out the e, that's why we did it, and we have LEN 2 equals 4r. Now we want to solve for that rate, so we take that 4r, actually I see what they're doing there is they want to make sure that you know why we cancel that. So we're going to put ln e, which equals 1. That's why it'll cancel. So 4r times 1 would be just 4r. Now we divide each side by 4. And we end up, with ln 2 divided by 4. ln 2, close the parenthesis. ln 2, close the parenthesis, divide by 4 equals 0.173. 0.173. Here we should have ln 2 divided by 4 equals r. So we know that the interest rate we need in order to double our money would be about 17.3%. That really helps you know where you've got to go with your money. Usually it'll be a high risk with that rate. What is the benefit of taking the natural logarithm of both sides of the equation rather than the common logarithm? Well, it creates ln e, which is equal to 1. Describe 2 different ways to use your calculator to check your answer. You could evaluate it by plugging this back into the original equation, right here. The other way you could do it is you could graph it as a system, and then you would graph y equals 1000 and y equals 500e r to the 4th. And you'd put it in as 4 times x instead of 4 times r. And put it in there, and then you see where the two systems intercept, and that will be your x value. That would be your rate. And I would expect you to fill that in down here on 2b, what I just explained. So go back and listen and fill it in. You're going to need that. Okay, so here comes another sample problem. You just want to practice these. In class you're going to practice a lot, so turn off the video and practice them without me and then with me and back and forth. Okay? So we know that log 3 equaling 2 would be 3 raised to the 2. We go by the definition of logarithms. Log 3 equals 2 means 3 raised to the 2nd equals whatever this is. Okay? So now 9 equals that. Subtract 1 from each side, x equals 8. So you can go back up and put 8 in there, and it would be log 3, 9 equals 2. I know that you can see that, but I want you to practice doing the math for it. So here we'd subtract 7 from each side. We're just trying to get the x alone. 7 from 10 is 3. And now we know 3 cubed, log 3 to this number equals 3. Then we know that it's 3 cubed equals 5x minus 4. That would be 27. So 27, now we'll add 4 to each side. We get 31. Divide 5 to each side. We get 6.2 equals x. How can you check your solution in part A? By substitution. Well, you can just show it. Log 3, 8 plus 1 equals 2. Log 3, 9 equals 2. Okay? Your calculator has keys for evaluating only logarithms with a base of 10 and e. Use the change of base property to rewrite the equation from part A so that the base of the logarithm is 10 or e. Then explain how to use graphing to check your solution. So we can do this fairly easy. From part A, that would be log 3, 9. So again, from change of base, that means it's log 9 divided by log 3. And then we plug it into the calculator, and we see log 9 divided by log 3 equals 2. Okay, so that equals 2, and that was the answer that we had originally for it. Okay, explain how you could use graphing to check your solution in part B. Well, again, you could graph these and look for the intersection. Graph the log 9 and graph the log 3, and then look for the intersection. That would just be two different log systems. Okay. Last page for notes, we'll do the practice in class, so don't worry about them. Let's go to this page of notes. Okay. On this page, they're solving a logarithmic equation by graphing. This is exactly what we were saying we could do on the last one. A telescope's limiting magnitude, m, is the brightness of the faintest star that can be seen using the telescope. The limiting magnitude depends on the diameter of the telescope's objective lens. The table gives two formulas relating m to d. One is a standard formula used in astronomy, the other is a proposed new formula based on data gathered from users of telescopes and various lens diameters. Okay, so this is the proposed, that's the original. So using a graphing calculator, enter 2.7 plus 5 log x for y1, 4.5 plus 4.4 log x for y2. Now it says graph the two functions in the same viewing window. So they give us, well, that will happen when we put in y1, y2. Use a window where x, let's see what our window is. X is 0 to 2000. The tick mark is every 100 units. Y is 0 to 20, and the tick mark is every 5 units. So we've got that set up. Now we hit graph, and there are the two graphs. Okay. Now, it would be almost impossible to see where those two intersect just by looking at that. So they tell us to go second, trace, and go down to intersect. And hit enter, and it will bring up right here where they intersect. They intersect, it says down here, at 1,000, 17.7 is your y value. 1,000 is your first value. So 1,000 millimeter diameter on the lens is what our two graphs agree upon. And it's kind of important to get the agreement there. What is the limiting magnitude that corresponds with the lens diameter? Well, the limiting magnitude would be your y value up there. The 17.7 would be the limiting value. And that would be in a magnitude. Okay, what equation can you write in order to solve the problem algebraically? Well, we would take the two equations that we just graphed. We would go 2.7 plus 5 log x equals 4.5 plus 4.4 log x. Okay, and now they want us to show how we do that. So just step through this with me. We draw our line. And the next thing I would do is gather the x's. I would subtract the where's the pen? I would subtract the 4.4 log x, subtract the 4.4 log x. This would cancel, and we would get log x 0.6 log x equals 4.5, and we still have the plus 2.7 here. So we subtract 2.7, subtract 2.7, and we get 0.6 log x equals roughly, what would that be, 1.8. I shouldn't say roughly, it's exact. Okay, and now we can divide by 0.6, almost done. Log x equals 3, because 0.6 will go into 1.8 3 times. And now we know that this is a base 10, so we say 10 to the third equals 1,000. And that's where we get our solution. Then we could plug it back in to get our 17.7. Okay, come to class ready to play some games. We're going to practice how to do these. You'll get it down really well. Come in with your questions on where I may have lost you during the film, but feel free to go back and study through it.